Okay, so this is an example of 3-1. Anytime you have a continuous function and you're looking for the absolute maximum and they've given you a closed interval, you always want to do this same procedure. First thing you want to do is you want to find the first derivative. So that's going to be 3x squared minus 6x minus 9. Now, we want to find the critical numbers for this. The critical numbers are either where this function doesn't, or its derivative doesn't exist, or equals 0. It always exists. It's a parabola, but it will possibly equal 0. So take that, set that equal to 0. Now, I notice that everything is divisible by 3, so let's do that. Anytime there's a greatest common factor, remove it. And then this becomes the quantity of x minus 3 times the quantity of x plus 1. So that means there are zeros at 3 or at -1. So all we have to do is we've got to plug in the endpoints and the critical numbers that are in that interval into the original function. Is 3 in that interval? No. So let's cross that one out. Is -1 in that interval? Yes. So we're going to use that. Okay. Now, again, you're plugging into the original function. So if we plug in -2 into our original function, we get -8 minus 12 minus 18 into the original function. We always, because we're looking for the biggest and the smallest in the original function. So we get -38. If we plug in 0, we get 0. Did I not, is it not -38? Oh, I'm sorry. Thank you. Thank you. So that would be -2. Yeah, I'm sorry. Ooh, had a rough day already. Anyway, if you plug in -1, you get -1 minus 3 plus 9, Mrs. Hot, and you get 5. So what can we glean from those values? Our smallest one is our minimum. So our minimum occurs at the point -2, -2. So if they ask, what x value will you have a minimum, you would want the x value -2. If they say, what is your minimum value of your function on this interval, it is a value of the output -2. This one here is our maximum. Our maximum occurs at the point -1, 5. So if they say, at what x value do you obtain a maximum, you would say -1. And if they said, what is the maximum height your function ever gets on that interval, it would be 5. And then you can pull it up into Desmos. You can take a look at that function and then just kind of think between -2 and 0. You could check to see where its max and min could be, okay? And that could check and verify your work. Yeah, I like that. 3.2 is about the mean value theorem. We're going to talk about Rolle's theorem and the mean value theorem to find certain values for a given function. So it is just an extension of what was happening in section 3.1, okay? So it's going to be similar. It's going to be similar. So Rolle's theorem basically says, if you have a continuous function on a closed interval, if it's differentiable on a open interval, meaning we can't necessarily have to differentiate at the endpoints, and the two ends are at the same height, then there has to be a first derivative equal to 0 within that interval. Okay, so let me say that again. If it's a continuous function on a closed interval, it's differentiable everywhere on the open interval. If the endpoints match, if their heights match, there must be an f prime of c that will equal 0 within that interval. Okay, here's why. Here, if the endpoints match and it's constant, every single one of those values has a first derivative equal to 0. Here, if they are the same height, it's continuous. If I connected them, I have to either come up or come down to come back up again. So there had to be a min or maximum or a function value where the slope of the tangent is 0. You can have more than one spot. It only guarantees that there's at least one of them. So if we're at the same height and we come up and come back down, we might get 2 values like that, okay? So then that leads us to this theorem that says, if our function's first derivative equals 0 between a and b, and it's always equal to 0 for all the x's in that interval, then f is a constant. And that's what we see right there. So if f prime of x equals 0 for all x's in the interval, then f has to be a constant. And that should make sense because you'll get a horizontal line. What's the slope of a horizontal line? 0. And that's where that comes from. Now, the one that's most important, I think this is the one that's going to help us, is the corollary, is used a lot. The corollary says if the derivatives are equal on a function f and g, then f minus g is a constant, or f of x plus g of x has to equal c. If f prime of x equals g prime of x on all x's within there, then f and g of x are kind of the same, but they might have, one might have had a constant added onto it. That's going to be very important because when we go backwards eventually from derivatives, we're going to account for the fact, well, I don't know what the function was. It might have been this, but maybe it might have had a constant on there that I was unaware of. And so that formula or that corollary will come back to us. For now, it's just kind of a result of some of the things we talked about earlier. So let's take a look at example 1. It says, does the following satisfy Rolle's theorem on the interval from -2 to 3? And if so, find c in the interval where f prime of c equals 0. Okay. So the first thing you have to ask yourself, is it continuous on that interval? Well, it's a cubic, it's a polynomial function, it's continuous everywhere, so yes. Second thing you say, is it differentiable? A polynomial is differentiable everywhere. So is it differentiable from -2 to 3? Sure is, it's differentiable everywhere. The next thing you check is, are we at the same heights on the endpoints? Rolle's theorem says we have to be on the same height at the endpoints. So we have to check, is f of 2 or f of -2 the same as f of 3? Are they equal? Okay. Well, if you plug in -2, and I've been real good at this today, you get 0. If you plug in 3, you also get 0. So that's a yes. If those 3 things are true, then we have to find c, where f prime of c equals 0. So what is f prime? And let's look at the zeros of it. So f prime of x is equal to 3x squared minus 6x minus 4. Now, where does that equal 0? Is that a factorable quantity? Is it factorable? Let's see, 3 times 4 is 12. The factors of 12 are 12 and 1. That doesn't have a difference of 6. 6 and 2, 3 and 4. Oh, we got to use a quadratic formula. That's grody. Anyway, let's use a quadratic formula. 36 plus 48 is 84. 6 plus or minus the square root of 84 over 6. Okay. If we do 6 plus the square root of 84, and then we divide that all by 6, we get 2.527. If we do a minus and then divide by 6, we get negative 0.527. Okay, so we need a C value in the interval. 2.527 is in the interval. Negative 0.527 is in the interval. So C could equal either 6 plus the square root of 84 over 6 or 6 minus the square root of 84 over 6. Okay, so it was a doable. I'm like, what? That has to be. Okay, so that's our C value. It is just a, where's the first derivative equal to 0, and what are the C's that are in that interval? Sometimes like one of them will work, but one of them won't. And sometimes you get more than one. If you looked at the graph, we said 2.5, don't. Or negative 5.27. If we looked at Decimus again, this one's at negative 5.27 and this one's at 2.52. So it should match up with the graph, or your algebra is weird. Okay. Now, the mean value theorem follows from the Rolle's theorem. The difference is that the endpoints don't have to match. And it basically says if f is continuous on that closed interval but differentiable on the open interval, there is some derivative that is equal to the slope of the line that connects the points. So this is the slope connecting the points. Okay, and then all they do for this version is they just multiplied both sides by b minus a. So they just cross multiplied that over. So you don't need to know both versions. I always just equal it to the slope, and then if they need me to rearrange it, I'll rearrange it. So let's look at what we've got here. So if we connected and found the slope of the line that connects them, there's some spot where the slope of the tangent is the same. If we connect them, there's at least one spot where the slope of the tangent is the same. That's all that that's saying, okay? So we don't need the endpoints to match for the mean value theorem. We do have to have the endpoints to match for the for Rolle's theorem because we're setting it equal to 0. For the mean value theorem, we're setting the derivative equal to the slope of the connecting line. Tantrum. Okay, so anyway. Okay, so the first thing we ask ourselves, is f continuous on negative 5 to 1? Yep. Second thing we ask, is it differentiable on negative 5, 1 without the endpoints? Yep. It's a polynomial. It's great. Okay. So the third thing we do here, though, is we find the slope for the endpoints. So it's just y f of 1 minus f of negative 5 over 1 minus negative 5. So it's just y2 minus y1 over x2 minus x1. What is the slope between the endpoints? F of 1 is 4. And help me, please, if I make a mistake. F of negative 5 is negative 50 all over 1 minus negative 5 or 1 plus 5. So we get 54 divided by 6, which is 9. So our last step is to set the derivative and look for where is it equal to 9. So for our Rolle's theorem, we are looking if the endpoints match where the slope is equal to 0, because that would be the slope of the line connecting them. But the slope of the line connecting these is 9. And so we're just going to set the derivative equal to 9. So the derivative is 3x squared plus 6x. And where is that equal to 9? Now we need, the c has to be within that interval. So if we have more than one option, we will actually need to account for that. Make that 3x squared plus 6x minus 9 equals 0. It is factorable by taking out a 3. And then we get x plus 3 and x minus 1. So x equals negative 3 or 1. Now, 1 does not count because it is on the endpoints. So we need to look at something within the interval. And so our C is negative 3. So if we were to pull up this graph and we drew the connector line between the two endpoints, and then we drew the tangent line when x is equal to negative 3, the slopes would match. Let's take a look at this. It says Calvin runs a 100-yard dash in 20 seconds. S of t is a function that gives his position from the start of the race. S of t is continuous and differentiable. Show that Calvin must have been going a speed of 5 yards per second at some point during the 20-second race. Well, 1, it's continuous. 2, it's differentiable. So the third step is, what is the slope between the start of the race and the end of the race, the 20-second race? So that would just be S of 20 minus S of 0 over 20 minus 0. Now, at the start of the race, he is not going any particular, he has gone no distance. At the end of the race, at the end of the race, he's gone 100 yards. At the start of the race, he's gone 0 yards. And then, so this becomes 100 divided by 20, or 5. So remember, by the mean value theorem, there is some C where f prime of C has to equal that value of 5. That is the connection of the endpoints. So by the mean value theorem, it exists. Do I know where it exists? Nope, don't care. This is just saying, yeah, it's got to exist somewhere within the function. And if we were given the function, we would be able to find it clearly using derivatives and stuff. We were not given the function, but it's just so that the endpoints give an average of 5. So somewhere along the route, he had an instantaneous value of 5 somewhere. Don't know where, but somewhere. Let's take a look at this one. Determine all the numbers C which satisfy the conclusion of the mean value theorem for the following function. So remember, it's continuous, it's differentiable. Let's find the slope between the endpoints. So we're going to do f of 2 minus f of negative 1 over 2 minus negative 1. If we plug in 2 to our function, we get 8 plus 8, which is 16, minus 2, which is 14. If we plug in negative 1 into our function, we get negative 1 plus 2 plus 1, which is 2. And then this is 2 plus 1. So we get 12 divided by 3, or 4. So what the mean value theorem says is that we can find a C where f prime of C is equal to 4. So let's go ahead and do that. Well, our derivative is 3x squared plus 4x minus 1, I think. 3x squared plus 4x minus 1. And where is that going to be equal to 4? Well, we're going to subtract 4 from both sides. We get 3x squared plus 4x minus 5. Does that look right? Yeah. And then we are going to, if it's factorable, factor it. If it's not, let's use quadratic formula, unfortunately. So it's negative b plus or minus the square root of b squared minus 4 times a times c is plus 60 over 2a's, or 6. Now 16 plus 60 is 76. Doesn't really reduce in any good way. So let's just do each one and see which is the inner in the interval from -2 to 1. -4 plus the square root of 76 divided by 6 is, so -4 plus the square root of 76 divided by 6 is about -2.11. -2 is not in our interval, so it's going to have to be -4 minus the square root of 76 all divided by 6. Let's see what that is. That is approximately 0.78. So our C value is -4 minus square root of 76 over 6, because that one was in the interval. So if you have the quadratic formula is necessary, always plug the two different values into your calculator. It might be that both work, but it's hard to say, okay? So that is Rolle's theorem. You don't have a lot of problems. Tomorrow in class, we'll work on the 3.1 and 3.2 homework, so you can work on it in class. Okay? There you go.